Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about vectors. Vectors, a very important topic in physics in general, Physics 107 in particular. Lots of the quantities that we deal with in this course, everything from position and velocity and acceleration to forces and momentum, they're all vector quantities, and so they're going to play an important role in our discussion this term, and the Wolfson textbook actually goes a little bit light in its discussion of vectors. It's just relegated to about 2 pages at the beginning of chapter 3, and that is not quite enough. So you may have learned about vectors in other courses, in math courses or other courses. And if so, that's great. If not, then this episode of What's the Big Idea is just for you. So let's dig in. Well, what is a vector? Well, simply put, a vector is a quantity that is characterized by both a magnitude and a direction. So, so a lot of the quantities we've been dealing with, magnitude and direction, things like position and displacement and velocity and acceleration, if they both have a magnitude and a direction, and now we're going to start considering motion that's taking place in a 2 and 3 dimensional world, and taking account the variety of different directions that things can point in is going to be central to our discussion. So we can represent typically a vector by an arrow. And of course, the direction in which the arrow points indicates the direction of the vector, and the length of the arrow is a measure of its magnitude. So, as we said, position is an example of a vector quantity. So here's an example. Imagine we're on some putting green here. Here's our golf ball. And generally, you want to pick some origin of your coordinate system. And we'll limit ourselves to a 2 dimensional world. So we have an X and a Y axis. And the position of the golf ball relative to this origin is indicated by this arrow here, and we refer to the vector, we'll call this particular position vector R1, and we'll write an arrow on top of the R to indicate that it's a vector quantity. And imagine that our goal is to get the ball into the hole. So after a successful putt, the position of the ball, position vector of the ball will be this arrow R2 here. And the arrow that connects the ball from its initial position to its final position we'll call delta R, and that stands for the change in the position or the displacement of the ball when it is putted. So we can write what's going on in this story is the final position of the ball when it's in the hole, R2, is equal to the sum of R1 and plus delta R. So the final position is equal to the initial position plus the change in position. So this example illustrates graphically what we mean when we talk about adding vectors together. This is an example of vector addition. So now let's define what we mean by the components of a vector. We can draw an arbitrary vector A with respect to some coordinate system, and we can talk about these two different components. This horizontal length here, which represents what we call the projection of the vector onto the horizontal axis. This we're going to call the x component of the vector A, or A sub x. And this vertical leg of this right triangle, and this is a right triangle here, the vertical leg we're going to call the y component of the vector A. So I can fully describe a vector in this 2-dimensional world just by telling you what the value of the components of the vector are. So as shorthand notation, which we'll use in this course, Wilson doesn't actually do this, but I find it convenient to represent the vector A just by specifying the components inside these angle brackets with a comma in between. And of course, we can use vectors to describe things in the three-dimensional world. So now we have, in addition to x and y, we have a z-axis sort of coming out of the plane of the screen. And here's an arbitrary vector r. And now to fully describe r, we need to tell you what all three of the components are. So I can write that the vector r in this case is the uh, x component, that's this leg here, that's the projection of r onto the x-axis, that has a value of 4.2 meters. The y component of this vector r, that's this length here, that has a value of 2.6 meters. And the z component, that's this length here, has a value of 3.2 meters. And it's always important to give the units here. I'm just going to write the units once, writing it to the right of our angle brackets. And it's important to note that components can be either negative or positive quantities. So here's an example here where this vector A has an x component, which is a negative number. The y and the z components in this example are positive numbers, but a sub x is, in this example, is a negative quantity. One more bit of notation to introduce here. Let's go back to our first drawing up here in this two-dimensional world. And you notice that, describing a vector in terms of its x and y components, those were sort of like Cartesian coordinates. But you could also fully describe a vector in a kind of polar coordinates by giving the length of the vector and the angle that vector makes with, say, the horizontal direction. So we can fully describe the vector A by giving its magnitude and direction. And the magnitude of the vector A, we'll use this notation to put an absolute value sign, and we're going to call that the magnitude of A. And in our drawing here, and a shorthand for the magnitude of A, which Wolfson uses, and it gets cumbersome to write uh, all these absolute value signs all the time. So if we just write the letter A without anything, that is going to correspond to the magnitude of the vector A. And you can see we've done that in this drawing here. This A here says that that's just the length of this arrow is the quantity A. And of course, we can go back and forth. Once we know the representation of the vector in Cartesian coordinates, you can deduce what the magnitude and direction are. So for example, we know that the magnitude of the vector A, just from the Pythagorean theorem, is going to be the square root of ax squared plus ay squared. And the angle theta turns out to be the arctangent of a sub y over a sub x. And similarly, if you know the length and direction of a vector, it's easy to find the x and y components. So we can write that the x component of the vector A is just given by its magnitude times the cosine of theta, right? Because here's a right triangle here, and this leg here is the hypotenuse of the right triangle times the cosine of theta. And similarly, we can write that a sub y is equal to the magnitude of the vector A times the sine of theta. So thinking in terms of components are useful for lots of reasons, but here's one example. When you go to add vectors, they make life very easy. So this diagram here shows graphically, if we have one vector A and a second vector B drawn in blue, and you take A and add to that B, you end up with the vector C. So what this drawing shows that if we know the components of A, the vector A, and the vector B, then to figure out the components of the vector C is very simple, because clearly from the drawing you see that the x component of the vector C is just the sum of the x component of the vector A and the x component of the vector B, and similarly the y component of the vector C, that's this length here, is just the algebraic sum of A sub y and B sub y. Or in other words, the vector C, which has components Cx and Cy, Cx is just equal to Ax plus Bx, and Cy is just equal to Ay and By, like so. Okay, so now let's talk about, we've talked about how to add vectors. Let's talk about how to subtract vectors. And before we talk about that, let me just remind you about the sort of what subtraction means just with ordinary numbers. So first, let's talk about what addition means. When we say something like 2 plus 3 equals 5, maybe we're taught to add in first grade or kindergarten or something like this, and you may have even been given this example. What we mean to add something is you could think about moving along a number line here, and when we say 2 plus 5 2 plus 3 equals 5, we start out with 2, you're 2 steps to the right of 0, and then plus 3 means you take 3 more steps in the positive direction of the number line, and you end up 5 units away from where you started. And when you talk about negative numbers, then when you add a negative number, you can think of that as adding a negative number is an instruction to take a step to the left. So when we say 2 plus negative 3 equals negative 1, what we mean is you start off 2 steps to the right, and then you take 3 steps to the left, and you end up at negative 1. And this is sort of what we mean by subtraction. 2 minus 3 is the same thing as 2 plus negative 3. So those should be all familiar ideas, maybe not from first grade, but from some point in your life. And now we just want to extend those ideas into a 2 and 3-dimensional world in which we're using vectors to take these directed steps. So this drawing here takes our previous example of we previously added A and B and got a new vector, which we called C, this green vector here. If we now want to subtract B from A, we want to calculate the vector A minus B. What that means is we go to the vector A, and then instead of stepping in the direction of B, we step in the direction opposite of B. So we're adding minus B, and this is A minus B here. And of course, the nice thing is that in terms of components, it all works out very nicely because we can write that the vector A minus B is going to have components. The x component of the vector A minus B is going to be AX minus BX, and the y component of the vector A minus B is going to be AY minus BY, like so. So the next thing is to talk about what it means to multiply a vector quantity by some scalar. A scalar is just a number. It can be a positive or a negative number. So let's give an example. Suppose I have some arbitrary vector A, which I'll represent by an arrow here. And what do we mean by, say, 2 times A? Just as 2 is a scalar. What's the vector? What do we mean by 2A? Well, the answer is uh, totally reasonable. The vector 2 times A just points in the same direction as A, but the arrow is twice as long. So multiplication by a scalar changes the length of the vector, but not its direction. And that scalar quantity can be a negative quantity as well. So if we wanted to talk about, say, minus 2 times A, that vector here, the negative sign is going to reverse the direction. So minus 2 times A points in the direction opposite to the vector A, and is twice as long as the vector A. Okay, so to see if you're following along, here's a quick thing to think about. I have two vectors C and D here, and I want to take the combination 2D plus C, and I claim that one of these five possibilities is a pretty good representation of the vector 2D plus C. Let you think about that. Hit pause on your playback of the video right now and think, and then we'll give you the answer in a minute. Okay, well, hopefully you've drawn a figure that looks perhaps, whoops, go back here, a figure that looks a little bit like the one I've drawn here. Because if we're going to add the vector 2D plus C, we first have to represent what the vector 2D is. And vector D points down and to the left, sort of like that. And then 2D is going to be a vector that points in that same direction, but is just twice as long. And then I'm going to add to that vector C, a vector that sort of points like this. And when I add 2D plus C, this is the result, this vector here. And I think if you look through all the possibilities, it's pretty clear from the possibilities that choice E is the one that is the correct answer. So hopefully you got that. So next, let's introduce this notion of what we're going to call unit vectors. And a unit vector, as the name sort of suggests, is just of any vector whose length is one long, whatever units you're in. So if you're talking about a position vector, if a position vector has a length of 1 meter, it is a unit vector. And this drawing here shows a three-dimensional world in which we've defined three very special unit vectors. And we're going to call these unit vectors I with a hat over it, J with a hat over it, and K with a hat over it. So we'll call these I hat, J hat, and K hat. And I hat is a unit vector that points along the X direction. J hat is a unit vector that points along the Y direction. And K hat is a unit vector that points along the Z direction. And this drawing also shows this vector R, which we've previously described. And R has X, Y, and Z components as such. Well, now that we know about unit vectors and we also know what it means to multiply a vector by a scalar, we have an alternative way of writing the vector R. So we can write in this example that the vector R I can write as 4.2 meters times I hat, because if we multiply I hat by 4.2 meters, we're going to get a vector that looks like this gold vector here. And now I can add to that 2.6 meters times J hat. Well, 2.6 meters times J hat is going to be a vector that points up in this direction and is 2.6 meters long. And then finally, we can add to this 3.2 meters times K hat. And that's going to be a vector that points in the K hat direction, but is 3.2 meters long. And adding up these three contributions here takes us to the vector R. So we can represent R either in terms of these unit vectors or this more succinct notation. The Wilson textbook actually uses this notation predominantly, which is fine. We'll often use this one just because it is a little bit easier to write. Okay, so I guess that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.